In this series of lectures, we will consider the design and analysis of counters as well as generic finite state machines. So first of all, with an announcement, all of this video material will be available on Vutela, and all of the class announcements will be available via Vutela. That's the main means of communication. So the assessment dates as well as the assessment type, whether it's going to be online or by submission, will be announced on Vutela. So the following series of lectures would cover what appears in chapter 9, and we will go through introduction to counters. We will go through what asynchronous counters are, and then we'll go through synchronous counters. You will note that synchronous counters are found in section 9-8-3 of the book, whereas asynchronous counters are going to be found in 9-2. And we will not follow the chronological sequences of the chapters as they are given in the book, but as you study, you are free to follow the sequence as you see it fit. However, in this class, we'll just cover 9.2 first, 9.3, and then in the subsequent lecture, we'll cover 9.1, 9.5, 9.4, go back to 9.5, and then 9.8. So just as a reminder, what we want to talk about is counters. So counters, as far as digital logic circuits are concerned, counters are a type of sequential logic circuits. When I say sequential, then it means there's an implication that they have memory. So they use memory in themselves. And our basic memory element in this case is flip-flops. So counters count, as the name suggests, which means they produce a repeating sequence of numbers. This is an example of a counter, and this is a 3-bit counter. 3-bit counter, we call it a 3-bit counter because the output count is going to appear here on Q0, Q1, and Q2. That is the output. Those are the 3 bits that through which the counter will count. The counter might also have a count enable input. You might also see what's called the terminal count output. Terminal count output simply goes high whenever the count has reached its maximum number, and then it will have, or because the sequential circuit will be triggered by a clock, so it will have an input trigger or a clock signal. So if the count sequence is like that, then we will say the count output is 0. If this is the case, then we will say the count output is 2. This would be 0, for instance. Now, you will notice that whenever we have a 3-bit counter, the counter can count up to 111. Now, because this number 111 is restricted by the fact that the counter only has 3 bits. So, in actual fact, if you have a 3-bit counter, it therefore means the counter can move from 000 to a maximum of 111. That is, it can move from 0 to a maximum of 7, which means the counter itself will have 8 unique states. 8 unique states, or 8 unique output sequences, so to speak. Now, because of that, we tend to call such a counter the maximum number of unique states which a counter can assume. We call it the modulus of a counter. So in this case, a 3-bit counter has 2 to the power 3 possible outputs, and if it counts all of those 8, if it reaches all of those 8 states or 8 counts, 8 sequences, we will call it an 8 modulus counter. The modulus of the counter would be 8. So it's worth noting that the number the maximum number of possible states for a counter is 2 to the power n. So this is an example of a timing diagram of a counter, our 3-bit counter. So our 3-bit counter, based on the clock, if it's positive, if it's triggered by a positive edge, as you can see here, whenever there's a positive edge of the clock, the count changes. So it starts by 0, 0, 0. On the positive clock, it changes from 0, 0, 1, which is 1. Remember, Q2 is the most significant bit and Q0 is the least significant bit. So on the other positive edge of the clock, then it will change to 0, 1, 0, which is 2. On the next positive edge of the clock, it changes to 0, 1, 1, which is 3, and so on and so forth. So in fact, the state sequence of the counter, this 3-bit counter, can be summarized using this table, whereby we say initially the counter would be at a reset state, which is 0, 0, 0, and then on the first clock pulse, it goes to 1, on the second clock pulse, it goes to 2, and so on and so forth. And on the 7th clock pulse, what happens, because it will have reached, it reaches its terminal count, then normally the terminal count output will go high. On the 8th pulse, what will happen is that the counter will go back to the original sequence, that it goes back to the initial 0 sequence. So it resets. Because now the counter, as we can see, can only take a maximum of 8 unique states, then we call the modulus of this counter 8. So this is an 8 modulus counter. The modulus of the counter is 8. Just as a reminder, I need to take you back to the operation of flip-flops. And the first kind of flip-flop that I would like to discuss is the D flip-flop. You will remember that the D flip-flop has the following symbol, is either this or that. And the D flip-flop, what distinguishes the two types here shown in the D flip-flop is that they will have this particular D flip-flop will have is triggered by a negative edge or the falling edge of the clock, whereas this particular one is triggered by the positive edge of the clock. So the D flip-flop has an input D, and input D will simply propagate to Q whenever it's been triggered. So for a positive edge triggered D flip-flop, if there is a 0 at the input on the positive edge, the 0 propagates to Q, the 0 will show up. If there is a 1 on the positive edge of the clock, the 1 will show up in Q after the rising edge of the clock. So the D flip-flop itself acts as a basic element of memory because it can recall its previous state. This is an example of a table that summarizes the operation of a D flip-flop. So you will see that this table has an input. An input is the two inputs of the D flip-flop. So this table is for a positive edge triggered D flip-flop. So the inputs are going to be the D input and the clock input. And the outputs of the D flip-flop, there's two of them. There's Q, there's Q bar. And because the D flip-flop has stores only a single digit or a single digit or a single binary number, it will only have two states, and the state will either be in reset state or the set state. The reset state is when the Q output is 0, the set state is when the Q output is 1. So what happens is, the way you interpret the table is that when you have D at the input and the D flip-flop is triggered by the positive edge of the clock, then the D will simply propagate to Q. If on the other hand the D was 1, on the positive edge of the clock, the D will simply propagate to Q. And of course, the Q bar will be the opposite of what Q is. So if you look at it in the form of a timing diagram, you will notice that so initially here, at this time, what happens is the D is 0, the Q will be 0, and the Q1 will be the opposite, which is 1. Now on the positive edge of the clock, what would happen is that whatever is in the D will simply propagate to the Q. So if there was a 0 in the D, the 0 will come to the Q. Because this was 0 and this was 0, this means the 0 will simply go into the flip-flop and show up as Q. So nothing will occur. There will be no change in the Q output. On the next positive edge of the clock, you will see as well that this was a 0 and this was also a 0. Now, what happens is when the clock goes high, it triggers this 0 to go to the Q, and this will therefore remain 0. Similarly here, on the positive edge of the clock, the number that's in Q here is going to be 1. Now, if this number is a 1, on the positive edge of the clock, this 1 will get transferred to the Q, and so on and so forth. So that's how to interpret the timing diagram of the D flip-flop. Another type of flip-flop which can be used is the JK flip-flop. You will recall that the JK flip-flop will have two inputs, J and another input K for data, and then you will have a dynamic clock input as well. And in this case, this is a negative edge triggered JK flip-flop. This is an example of a negative edge triggered JK flip-flop. This one is negative edge. So which means the clock will trigger this JK flip-flop on the falling edge instead of the rising edge. However, in the table here, I'm giving you a table for a positive edge triggered JK flip-flop. Because of that, the symbol for the positive edge trigger would be an arrow that faces up. If it was a negative edge trigger, normally the symbol would just be an arrow that faces down. So the JK flip-flop, on the other hand, will have 3 distinct transitions. It will have 3 distinct transitions. The first one is called a no change, which means it doesn't change. There's no transition at all. It remains as it is. The second one is a reset, where the Q output is 0. The next transition is when you have a Q going to 1, which is a set transition, and following that you have a toggle transition. Toggle transition simply means the state flips. If Q was 0, it then becomes 1. If Q was 1, it then becomes 0. So the output would simply be the opposite of what it was before. So what's important here to remember is that what are the inputs JK that force these different types of transitions. So JK, when JK is 0, 0, when the input J and the output K are both 0, the JK flip-flop would have a no change transition, which means it will not change when both of them are 0. When J is 0 but K is 1, then the JK flip-flop will go into a reset state. On the other hand, when J is 1 and K is 0, the JK flip-flop will go into a set state, which means the Q output will be 1. If on the other hand, the JK flip-flop inputs are both 1, the transition that it will go to, it will toggle. So it will depend on what it is storing. If it was previously storing a 0, if it was previously storing a 0 and the inputs are 1, 1, the next output will be 0. If it was storing a 1 and the inputs are 1, 1, the next output will be 0. If you are storing a 0 and the inputs are 1, 1, the next output will be a 1. So it will toggle. It will simply flip the state. So toggle simply means it flips the state. And because of that, we can clearly see a demonstration of memory here, that the JK flip-flop remembers the previous state and is able to change into the next state, depending on the inputs. So in terms of counters, there are two types of counters. The first type is called an asynchronous counter, and the second type of counter is called synchronous counters. For now, we will simply look at asynchronous counters. So this is an example of a 2-bit asynchronous counter. So what do we mean by an asynchronous counter? Asynchronous counter, we mean a counter where the flip-flops, the memory elements, do not share the same or common clock signal. So the flip-flops do not have the common clock signal, which means they're not triggered by the same signal. In this example, so in this following circuit, you will see this is an example of what's called an asynchronous counter, a 2-bit asynchronous counter. And you will notice that the input of the first flip-flop, flip-flop number 0, the input is going to be from the clock signal. On the second flip-flop, the input is Q not bar, which means the clock signal of the second flip-flop and the clock signal of the first flip-flop do not come from the same input signal. And because of that, this is called an asynchronous. It's called an asynchronous counter. So for asynchronous counters, what tends to happen is that because the clock signals are different, they also do not tend to change the state at the same time. So the flip-flops don't change the state at the same time. They do not transition at the same time. And sometimes because the state of later flip-flops, like flip-flop 1, is affected by the input of the earlier flip-flops, these type of counters are called triple ripple counters, because it looks like the input ripples from the clock. The clock influences Q0 and Q0 bar. That in turn influences the clock input of flip-flop 0, which in turn influences Q1 and Q1 bar. Because the state seems to ripple from Q0 all the way to, from flip-flop 0 all the way to flip-flop 1 and the other subsequent flip-flops. This is sometimes called a ripple counter. Let us for a moment consider now how the asynchronous 2-bit counter should operate. So in the previous slide, we have emphasized that because this is an asynchronous counter, it means the input clock signals are not shared by all of the flip-flops, which means the flip-flops are not triggered by the same clock signal. So in this case, we see that flip-flop number 0 is being triggered by the clock, by external clock CLK. However, flip-flop number 2 is being triggered by the output of flip-flop number 1. So it's being triggered by Q0 bar. Now, taking a reset position, let's say initially both of the flip-flops have stored a 0. So both of them have a 0. Now, what will happen is that the input of flip-flop 0, that is the D0. If we have here if let's say I was to draw D0 here, and then I was to consider D1. At the beginning, D0 would be equal to 1. Because if you look at it, D0 is connected to Q bar, Q0 bar. So at the beginning, Q0 would simply be 1 because D0 would simply be 1 because Q0 is 0. Let's trace back also D1. D1 is connected to Q1 bar. So which means that if Q1 is 0, then D1 is going to be 1. Now what will happen is at the positive edge of the clock, now whatever is in D0 will go to Q0. So whatever is in D0, that is a 1, will now come to Q0. So Q0 will rise because of that. Now at that particular moment, remember flip-flop number 1 is being triggered by Q0 by Q01. So Q01 itself, as Q0 goes from 0 to 1, Q01 will simply dip. So it will have a negative edge. Therefore, flip-flop number 2, which is this one, the second flip-flop, which is flip-flop number 1, flip-flop number 1 will not be triggered in this period. It will not be triggered in this period. Now, at the following rising edge here, on the next rising edge of the clock, what would have happened? What would have happened is, if we look at flip-flop number 0, we will see that since Q0 would be 1 here, it means that D0 would be 0. So when the next clock moves, on the positive edge of the clock, that 0 would now change into Q. It will move from D0 all the way into Q, which then means now the flip-flop number 0 will flip its state. On the other hand, as this edge is happening, this negative edge of Q0 will result in a positive edge of Q0 bar. So Q0 bar, which is the clock signal of flip-flop number 2, will have a positive edge. And this positive edge will trigger whatever is in D1, which is basically 1, it will trigger that 1 to go into Q1. Right? So if we follow that sequence, because you will notice two things here. You will notice that, first of all, it takes time there's a finite amount of time for D to propagate into Q. There's a propagation delay because the circuits themselves will have propagation delay. And also you will notice that because the clock signal of F1 is attached or is controlled by the output of flip-flop 0, there are two sets of delays that will occur before the state of the second flip-flop, which is flip-flop number 2, actually settles to the final value. So there's a single propagation delay here for the state of flip-flop 0 to change. However, there will be two propagation delays here for the state of the second flip-flop number 1 to change. If there was a third flip-flop also, it therefore means that it would only change after 3 units of propagation delay. And this also goes back to the explanation which I said earlier, that because of this propagation of the state from flip-flop 0 to flip-flop 1 and subsequent flip-flop. This is normally called a ripple counter. So here is an example of a 3-bit counter. So for a 3-bit counter, what I want you to note is that for a 3-bit counter, the input, the first flip-flop will have the input directly from the clock. The second flip-flop will have the input from Q0 bar of the previous flip-flop. The third flip-flop, which is F of 2, will have the input of Q1 bar, which is from the second flip-flop. So the state of the flip-flop is that the clock will trigger flip-flop 0, flip-flop 0 will trigger flip-flop 1, flip-flop 1 will also trigger flip-flop 3. And then this is how then the state will ripple through. The state will ripple through from flip-flop 0 all the way to flip-flop number 2. And this, in this example, it will give you a 3-bit counter. However, you will notice that because the propagation delay is normally very small, in the timing diagram we tend to ignore, even if it's an asynchronous counter, we tend to ignore that propagation delay, because here you see that it looks like immediately as the clock edge goes positive, then the flip-flop 0 bit Q will change, which is not necessarily true, because there is a slight propagation delay here. There's a slight propagation delay here, and there's also a much bigger propagation delay here, and a much bigger propagation delay here of three propagation delay units. So going back to this propagation delay, we will emphasize that it takes a finite amount of time for the clock to take effect. That is, when the clock changes, the input here takes a certain amount of time to reflect at the output. And this is because of the propagation delay of the logic gates that make up the flip-flop itself. Now we know that from the previous module that propagation delay can be defined by the propagation delay from low to high, or the propagation delay from high to low. And sometimes, of course, they are different, but the propagation delay of a circuit is normally given as an average of this. So let's say, for example, here they are the same, and this propagation delay amounts to 10 nanoseconds. Then it means that in order for this ripple counter that we are looking at, this example ripple counter that we are looking at, to settle, it means we need to account for a propagation delay here of the first flip-flop, and the propagation delay plus the propagation delay of the second flip-flop. Because remember, the second flip-flop is triggered by the first flip-flop. So we need a total propagation delay of, it takes a total propagation delay of 20 nanoseconds in order for the output of the counter to show after the clock has triggered it. Because of this, asynchronous counters have a disadvantage, in the sense that the maximum frequency with the fastest clock that can be used for this particular counter, because it has two flip-flops with a propagation delay of 20 nanoseconds, the maximum frequency would be 1 over 20 nano, which is simply equal to 50 megahertz. So if the clock is faster than 2 megahertz, then the clock would change. The clock changes would be too quick for them to all reflect on both on both of these flip-flops. So the counter might miss its sequence. So sometimes in asynchronous counters, we may want to truncate the count. That is, we may want to count to a certain number, but not all through all of these states. And when that happens, we use a technique called partial decoding. This is an example of a partial decoding technique of a counter whose count has been truncated. This is a decade counter, a BCD decade counter, which should have modulus of 10. So we want the counter to count from 0 and to 9. And for it to count from 0 to 9, we will need 4 flip-flops. The reason why we need 4 flip-flops is because 2 to the power 4 is equal to 16, which means this is enough to count up to the 10 that we want. We cannot use 3 bits. 3 bits would not work because 3 bits would give us 2 to the power 8, would give us 2 to the power 3, which is equal to 8 states. So the 8 states is much less than 10. So it won't work. So in order to remedy the situation, you need to use 4-bit counter. However, you have to truncate or stop the count whenever it gets to above the value that you want. For instance, in this case, we have a counter here, Q3, Q2, Q1, Q0. So our counter will have these outputs, Q0, Q1, Q2, Q3. So we want, when the counter encounters a state 10, the binary number 10, we want it to go back to 0. Whenever it encounters the binary number 10, we want it to go back to 0, to reset, basically, so that we stop this count. And because that's the case, it means, simply speaking, we need to detect when the counter has a high Q1 and a high Q3. Whenever a counter has a high Q1 and high Q3, we need to clear that counter. And the way we do it is to use this decoder circuit. The decoder circuit in this case is simply a NAND gate. And so the NAND gate is connected, one input is connected to Q1, the other input is connected to Q3. So whenever you detect a 1 and a 1, this is a truth table for a NAND gate. So whenever you detect a 1 and a 1, that is, in this particular instance, the output of the NAND gate would be 0. So you'll get a 0 here, and this 0 is going to reset your counter. It's going to clear everything here, and the count will start back at 0. So the counter will go from 0 to 9, and as soon as it tries to enter the state 1010, it will simply just go to glitch and simply go back to 11. So in that case, this asynchronous counter will have a modulus of 10 instead of 16. So here is an example showing what's happening here is that what would happen here is that at this particular stage, you see our output count is 1, 0, 0, 0. So it's 1, 0, 0, 0. This is a negative edge triggered asynchronous counter because of this. The negative edge asynchronous counter. So as soon as we have another negative edge coming in, then this count will increase. This is going to be 1. So our count is going to be 1, 1, 0. Sorry. 1, 0, 0, 1. So this is the final count, which is supposed to be 9. This is 8. So at this moment, when the count is 9, at this moment when the count is 9, what will happen is that in the next state, as you experience another negative edge of the clock, the counter will attempt then to go to 10, which means it will attempt to have for a moment it will attempt to have a particular state where it has a 1, 0, and then it will attempt to put up a 1 here, and this will attempt to become a 0. So the moment it does that, the moment this 1 comes up, it will just combine with this 1 into the NAND gate. So the NAND gate will have 1, 1, and it will start producing a 0. The moment the NAND gate produces the 0, this NAND gate will simply clear everything that's there. So it will simply clear this, which means that will show here as a 0, and this glitch will then force all of these flip-flops to go back to 0, 0, 0, 0. So another example, alternative design of counters, we said it's what's called synchronous counters. And in synchronous counters, what happens is that the distinguishing characteristic is that all flip-flops share the same clock signal. So in this case, you will see that the clock signal goes to flip-flop number 2. The clock signal also goes to flip-flop number 1. The good thing about this is that it means, therefore, that all of these flip-flops are triggered at the same time, and therefore they are synchronized. Because of that, we call this counter a synchronous counter. And the interesting bit about the synchronous counter is that the inputs of the flip-flops are determined by a combinational logic circuit. So a combinational logic circuit will determine the inputs of a circuit. This, if we contrast, this is an example of an asynchronous counter. It's asynchronous because the clock here is only connected to the first flip-flop, and the second flip-flop has a different clock. If you compare that to this particular case where the clock, it's from both, the same clock goes into both the first flip-flop and the second flip-flop, you will see the difference between the two, synchronous and asynchronous. Now the challenge here for synchronous counters is, how do you then determine this input combinational logic circuit to make the computation? How do you determine this input combinational circuit that will determine the next state of your flip-flop? And this challenging problem requires a systematic design process. And this we will later learn in the section where we study the design of a finite state machine. For now, we look at an example of a 2-bit synchronous counter, and we see that the sequence, the counter here, it has a sequence of dependent state, and the key here is that a combinational logic circuit creates the next state. So we'll see that if your present, so the counter will go through a series of next transitions. So the transition, if we have a transition table here of a counter, we'll see that if the next state is 0, 0, the current state is 0, 0, it means it will then transition to 0, 1. If the current state is 0, 1, it will then transition to 1, 0. If the current state is 1, 0, it transitions to 1, 1. If the current state is 1, 1, it will transition to 0, 0. And this is an example of how then a 2-bit counter would generally work. But because this is an asynchronous 2-bit counter, we can see, if we analyze the combinational logic, that the input of the input D0 in this case, it's simply Q0 bar, whereas the input D1 is an XOR or an exclusive OR of Q0 and Q1. So it's an exclusive OR gate of Q1 as well as Q0. And this is how, as a reminder, an exclusive OR gate works. An exclusive OR gate works by giving output of 1 whenever the two inputs are different. So we can analyze the behavior then of a synchronous counter in this instance, that if, say, for example, initially we were at 0, 0, if initially we were at 0, 0, what will happen is that the next state will have to be 0, 1. So the next state will have to be 0, 1. So what will happen is the clock signal, when we are at 0, 0, the inputs are going to be here. The input here is going to be 1. The output here is going to be 1 because the input, because the flip-flop 0 will have 0 and this will have 0 initial. It means Q0 bar would be 1, would have a 1 here, and we would also have a 0 and a 0 at the input. So it means we'll have a 0 here at the input. Now, as the clock goes high, what will happen is that this one will be taken into the flip-flop. So Q0 will tend to rise. However, Q1, because the input at D1 would be 0, it will remain as it is. It will remain as 0. The operation of this 2-bit counter can be analyzed using the table below, which has the clock input, the present or current state, and then how the current state affects the flip-flop inputs, and then how those flip-flop inputs will transition to form the next state. So we can analyze this by first considering, or by remembering, that D output D0 is equal to Q0 bar. So D0 is equal to Q0 bar, and D1 is connected to an exclusive OR input, which comes from the exclusive OR of Q0 and Q1. So D1 is equal to the Q0 XOR Q1. And we said the exclusive OR gate, the way it operates is by giving out an output of 1 whenever the two inputs are different from each other. Now, what needs to happen is, in our analysis, we'll analyze beginning from the left all the way to the right. So we will see that the next state Q1 is affected by the input D1. Now the input D1 itself would be the exclusive OR input of Q1, which is 0, exclusive OR Q0. So it will be Q1 exclusive OR Q0, and this would give us 0. So D1 would be 0, and because D1 would be 0, it means therefore that Q1 in the next state would be 0. Right? Now, for D1 would be the opposite, would be Q0 not. So this will flip Q0. So because Q0 is 0, D0 would be 1. because Q0 0, Q0 bar would be 1. Therefore, it means that the next state of Q0 is going to be 1 itself. In a similar case, here we are going to have D1 as 0 exclusive or 1, which is 1, which means Q1 in the next state is going to be 1. For D0, we look at that. We say D0 would be 0, which is the opposite of Q0. And therefore, because of that, we'll have 0 here. And then in this case, we have D1 as 1 exclusive OR of 0, which is 1. And because of that, we're going to have the next state as 1. For Q0, we have a 0 here, which means the inverse of that is going to be a 1, or the complement of that is going to be a 1. And because we have a 1 here, the next state is going to be a 1. And in this instance, we have a 1 exclusive OR of a 1 and a 1, which are these two inputs. This will give us a 0. This means the next state, Q1, would be 0. And then here we have a 1, which means your Q0 bar is going to be a 0. And because of that, we're going to have a 0. And so we can be able to analyze this, we can be able to analyze how the synchronous counter will function in this way. This analysis will be particularly important when you try to design the combinational logic circuit that controls the next state of the synchronous circuit. In a similar manner, we can also analyze this example of a 3-bit synchronous counter, but this synchronous counter in this case is being made using JK flip-flops. So for JK flip-flops, this is a reminder of a transition table for a JK flip-flop. Remember, when all inputs are high, we have a toggle state. When all inputs are low, we have a no change. These are the most important states. We'll see why later. And if we look at the combinational logic inputs here, let's look at J1, J0, K0. So J0 and K0 are always high, which is 1. And then J1 and K1 are also from a common input, which is Q0. J2 and K2 are from the end of Q1 and Q0. That's that. So because we have such a circuit where J and K are always the same, it means our transition table, we are concerned more about this transition and that transition. Now, if we analyze the first row, let's look at the first row. So if you just simply look at that first row, okay, let me use a different set of marker here. So we use this, look at the first row. So on the first row, analyzing it from left to right, we see that we have, if we look at J2 and K2, J2 and K2 are equal, and J2 and K2 are the end between Q0 and Q1. Q0 and Q1 is 0 and 0, which means these are going to be zeros as well. Now, because we have 0 and 0, it means flip-flop number 2 has 0, 0, which means it will have no change, which means its next state flip-flop number 2, Q2, the next state will be 0. It will be whatever the previous state will be. Q1, Q2. And then if you look at J1, K1, excuse me, you will see that the inputs J1 and K1 is simply Q0. So Q0 is 0, which means the inputs of K1 and J1 are going to be 0, 0. And because they are 0, 0, we will have from the transition table, 0, 0 is no change. So we'll have a no change, which means Q1 will remain, and Q1 will remain as 0. The next one we look at Q0. So J0 and K0 are 1 because they are always 1, effectively. Because there is always 1, it means it will toggle. So which means it will flip the state. Now, if we look at Q0, the previous Q0 here is 0, which means now we expect this to be a 1. And then we can follow the same logic throughout these rows. We will see that it gives us a behavior that counts. This, for instance, is a similar behavior. That's the one that we have just analyzed. It's a no change toggle. So which means in this case, Q2 will remain as 1, Q1 will remain as 0, and then the other one will toggle to 1. And so on and so forth. So you can analyze the synchronous counters from left to right by looking at the outputs in the current state, how the outputs affect the inputs of the flip-flop, how the inputs of the flip-flop affect then the transition of the flip-flops, and what the transition will give you as the next state. Please do go ahead and practice problems which are relevant to sections 9.2 and section 9.3 in the reference book. Do that for revision, and in the next part of the lecture, we will continue by looking at what finite state machines are. Thank you.